So it's a pleasure today to have Sasha Sodin from Queen Mary University in England. And he's going to let us know about lower bounds on the eigenfunctions of random Schrodinger operators in a strip. Sasha?
Okay, thank you very much. It's a pleasure to speak at this nice seminar. This is based on joint work with Ilya Goldsheid. And basically the question I'm interested in is whether an eigenfunction of a random Schrodinger operator in the localized regime has an exact rate of exponential decay. It's known to decay exponentially, and the question which is less clear is whether there is an exact exponential decay, and I will try to report on some modest progress in the quasi one-dimensional setting. So let me start slowly. We start with a random Schrodinger operator on a lattice lambda. Well, usually lambda is z to the d, where d is some small integer, and in this talk the main focus will be on a strip, the cross product of z and a finite set, and even perhaps on the half strip, which is the product of the positive integers and a finite set. Then to each side of the lattice, we associate a random variable. We assume that these are independent and identically distributed, non-constant, and let's say with a finite fractional moment. And then we construct our Schrodinger operator on L2 of lambda, acting as usual by h psi of x is the sum of overall neighbors of x of psi of y plus v of x psi of x. Okay. I'll briefly discuss the higher dimensional setting, which is very interesting, but I don't have much to say about it. Most of this talk will be about strip and in this case for Z or for the strip, and then also for half strip, the spectrum is known to be a pure point. Let me give the references for W equals 1. This was proved for nice distributions by Goldsheid. Molchanov and Pastor in 77, and for general distributions of V by Carmona, Klein, Martinelli in 87. And for broader strips, the case of nice distributions was first studied, was settled by Goldsheid in 1980, and the general case by Klein, Lacroix, and Spice in 1990. So in these works, it was proved that the spectrum is pure point. It's also known that in all of these cases, the eigenfunctions have exponentially decaying. The first result of this form for the one-dimensional case is due to Molchanov, but there are many further references, including these works. and let me just write the statement that the upper limit of the logarithm of an eigenfunction divided by x is less than 0. And what's important, that this is true for all eigenpairs lambda psi with probability 1, and these are the quantifiers which you want to have throughout the stock. The quantifiers will be that some statement is true for all eigenpairs with probability 1. Okay. So this is what is known, and a bit more is known too. What I would like to know is whether this lim sup is actually a deterministic limit. Is there, so the question is there an exact rate of exponential decay, and what it is? So in the case of a strip, it's physically obvious what the answer should be. So let me introduce some notation first. So we're in the case of a half strip, which looks like this. This is layer 0, layer 1, layer 2, and so forth. If psi is a function on the strip, I will denote this chunk of size 2w by psi arrow of n. Psi arrow of n is a 2w dimensional vector composed of 2w consecutive coordinates of psi. And in this case, common sense and a variety of heuristics, including the Fermi-Gödel rule, indicate that the limit should be a deterministic quantity. The limit as n goes to infinity of this expression, the logarithm of the norm of psi of n divided by n should be a deterministic quantity, which I'll define formally in a few minutes, which is called the which is the negative of the slowest Lyapunov exponent. The slowest Lyapunov exponent. And again, I insist on the quantifiers. I would like this to be true for all eigenpairs lambda and psi with probability 1, and this is let's call it a conjecture. So I don't have a reference, but so I don't want to claim more than what is written, but I've heard from many people that this was discussed in the 80s when people were working on the strip, but the problem, as I'll try to tell, is not settled so far.
So excuse me, a naive question. So this is not an upper bound. It's all eigenvectors decay the same way.
Yes. So I mean the Lyapunov exponent depends on the energy, but it
depends on lambda. So sorry, I missed that.
Yeah, it depends on lambda. But yeah, the upper bound is known. As I will say shortly, the upper bound is known. The question is why can't they decay faster? So all the rest of the talk will be about the strip. So let me now make a brief comment on higher dimensions. In higher dimensions, d greater or equal than 2, it's known that there are regions of Anderson localization, regions of pure point spectrum, which have been formally established by Fröhlich and Spencer, and later by Eisenman and Molchanov in the 80s and 90s. So let's fix an interval of where this is the situation where we have a pure point spectrum with exponentially decaying eigenfunctions. Then very naively, I would expect that the logarithm of psi of x behaves at infinity. Perhaps, okay, I put quotation marks here, as minus some homogeneous quantity depending on x. Perhaps it's a norm or a quasi norm. And again, this should be true for all lambda psi where lambda lies in I. Perhaps there are some exceptional points. Perhaps there are some sparse set where this is violated. So I don't insist on the precise meaning of this quantity. What I do want to say is that I'm not aware of any results at all, not even with other quantities. I mean, I would like to have it with these quantifiers, but I'm not aware of any results in the direction of sharp rates of exponential decay in 2 dimensions and above. So not only of this. So basically, at least to me, nothing is known, and I don't have a good idea how to approach this. Okay, so from now on, I'll return to the strip. Are there any questions? Is the question clear up to the definition of the Lyapunov exponent, which will come in a second?
I think it's clear.
Okay. Good. So now let me remind the definition of the Lyapunov exponent. So we look at the formal solutions of we fix lambda, and we look at the formal solutions of the second order equation h psi of x equals lambda psi of x. Then it's a second order equation, so clearly there is a matrix which takes which I'll denote Tn of lambda, which takes psi of n. I remind you that psi of n is this chunk, and moves it takes it to the next chunk, psi of n to psi of n plus 1. And explicitly, this transfer matrix is given is a 2w by 2w block matrix given by lambda times the identity minus v of n minus the identity 0, where v of n is this w by w matrix having the potential on the diagonal v of n, v of w, v of n1, v of n w, and ones above the diagonal and zeros everywhere else. Okay, and then we construct the n-step transfer matrix phi n of lambda, which is the product of n of them, Tn minus 1 of lambda up to T0 of lambda, which takes the initial condition psi of 0 and moves it n steps forward. Okay, so the Lyapunov exponents are defined, gamma j of lambda are defined as limits. Well, they measure the exponential growth and decay of the singular vectors of the transfer matrix. So we look at the jth singular value of the n-step transfer matrix. We take its logarithm, and then we take the expectation and divide by n and pass to the limit as n goes to infinity. This is by definition the nth Lyapunov exponent. In the definition, we have the expectation over here, but it is also known to be equal to the almost sure limit of the same expression by Furstenberg-Keston or whatever. Okay, so this is the definition, and one can easily see that our transfer matrices are symplectic. They lie in the 2w by 2w symplectic group, and which implies that singular values come in pairs S1 over S, and therefore the Lyapunov exponents come in pairs gamma minus gamma. So gamma 2w is equal to minus gamma 1, gamma 2w minus 1 is equal to minus gamma 2, and so forth. The main fact in this theory, due to Goldsheid and Margulis, which is used in all the proofs of localization, is that all these exponents are distinct. Gamma 1 is strictly greater than gamma 2 and so forth, up to gamma w, and this is strictly greater than 0. So all the exponents are strictly positive. The fact that the first one is positive is in the earlier theorem of Furstenberg. So let me draw a picture and try to explain why the rate of decay of the eigenfunctions should be given by this smallest positive Lyapunov exponent. So the picture is based on this theorem and also on a theorem of the connection between the picture which I'll draw and the formula which I wrote is based on the theorem of oscillators, which I didn't state, but the picture is correct. So for w equals 1, it goes as follows. We have we have two singular values. One is exponentially growing, one is exponentially decaying. So we have a decaying direction. We have in our two-dimensional plane of initial conditions, we have a decaying direction. If we start there, then the solution decays exponentially with rate gamma 1. If we start with any other initial condition, we have exponential growth. This vector of pure growth will be denoted by u1, and this vector of decay is denoted by u2. These are the right singular vectors of the transfer matrix. And as you see, they are orthogonal to one another by construction, more or less. For w equals 2, we have a two-dimensional plane. So we have a two-dimensional plane of decay in initial condition, and all the rest grows. So we're in four-dimensional space, so it's a bit tricky to draw. Here, this is the two-dimensional decaying plane, and inside this decaying plane, we have the vector u4 of fastest decay. If we start at u4, the rate of decay is given by the by gamma 4, which is minus gamma 1. We have fast decay. If we start with any other initial condition in this decaying plane, the rate of decay will be given by gamma 3, which is minus gamma 2. Now we also have, if we don't start in the decaying plane, we have exponential growth, and particularly we have the two other singular. So let's denote. We have the two other singular vectors u2 and u1. This is the plane of pure growth. And what is perhaps less clear, but correct and very easy to check, is that this plane is obtained from this plane by a symplectic rotation. So the symplectic rotation takes them to one another. Okay. So what is the naive way to understand Anderson localization in a strip? We're in a half strip, so we have let's say Dirichlet boundary conditions. So we have a space F of things which vanish on the boundary of legal initial conditions. So this is a W-dimensional space of initial conditions, living in the 2W-dimensional space of all possible initial conditions. Also, we have this decaying, plane, or in general decaying W-dimensional space. That's denoted by E lambda. It's again, it's a W-dimensional space of decaying initial conditions. These are two W-dimensional spaces in a 2W-dimensional in R2W. Usually, two planes in a 4-dimensional space generically would not intersect, right, by dimension count. The generic situation we expect is that the intersection will be trivial. So generically, we would expect that F intersection with the lambda is 0. What this means is that for any initial condition in the legal space, we have exponential growth, and then clearly we cannot have this cannot be an eigenfunction and not even a generalized eigenfunction. So yeah. So why do we have eigenfunctions at all? And the naive way, so the naive way to think about eigenfunctions is as follows. Well, we're not interested in one spectral parameter lambda. We vary lambda. Lambda is real, so it varies along the one-dimensional set. So we have an additional degree of freedom. We have a one-dimensional family of pairs of planes in the 4-dimensional space, and then we expect as we vary lambda, there is a 0-dimensional exceptional set of lambdas for which the intersection is non-trivial, right? And if everything is generic, this is naive, and as I'll explain briefly, this is naive and wrong. But if everything would be generic, if you have two W-dimensional spaces in a 2W-dimensional space, and they're generic, and they also depend on the parameter, we expect a 0-dimensional set of parameters where they intersect. And you would think that these are exactly so. For these parameters in this exceptional set, you do have a legal initial condition for which you have a decayed solution, and this is your eigenfunction. So the eigenfunction decays exponentially. So we kind of expect that these are the eigen values, and for them we have exponential decay. Now, of course, if we are in this situation, so our space F of initial condition does intersect this decaying plane, it's highly unlikely that the intersection will be on this fastest decaying direction. We expect the set of lambda is varying in a one-dimensional set, so we expect the intersection to be generic. Right, there's no reason to expect the intersection to lie in this higher quad-dimensional subspace. So by the same naive logic, we expect the intersection to be generic, which means that the decay is the slowest possible one, the one that we have generically in this plane, which means that it should be given by the slowest Lyapunov exponent, and if you believe in these two statements, then you should believe that this conjecture is true. Any questions? Is this okay? Any questions or comments?
There seems to be no questions. Everything is clear, or at least clear enough.
Or everyone is already lost. And, yeah. Okay, good. So now let me explain why this is wrong. If this is clear, then I should. Yeah. So what is wrong here? What is except for the fact that this is unproven, it's also wrong. What is wrong? if we go back to the definition of the Lyapunov exponent, we see that this is an almost sure limit. So for fixed lambda, this equality holds almost surely. But we have a continuum of lambdas, and it's not clear that we can take a union bound over for a continuum of events of full probability. Right, it's not clear that the intersection of a continuum of events of full probability is a full probability, and indeed it's not only unclear, it's also why is gamma g of lambda equal to the limit of for all lambda simultaneously. And indeed, it turns out that this is wrong. So this was first proved by Goldsheid in 75 for the one-dimensional case. I mean, all the published works which I'm aware of are for W equal 1, but I'll state the result, the correct result for wider strips. There are many subsequent works and recent generalization by Gorodetsky and Klepson. And it states the following: fix a number tau between 0 and 1. Let's you can assume that it's so it may be even 0. So you can think that the statement which I'll write now is strongest when tau is 0. So you can just imagine that it's 0 for now. Consider the following exceptional set of lambdas for which not only this limit is not equal to what it should be, the limit of defining the wth Lyapunov exponent is not only not equal to what it should be, but in fact the lower limit is smaller than tau times gamma w of lambda. So again, if you set tau to be equal to 0, there is a direction which doesn't the wth singular value doesn't grow exponentially at all. This is of course a very annoying situation when all this isolated picture collapses. You don't have exponentially grown and exponentially decaying directions. And the statement is that B tau is dense in the spectrum with probability 1. So again, in the published works, it's stated for W equals 1, but it's true for strips of arbitrary width. So there is a set. It's not very large. It's well, Gorodetsky and Klepson showed that it's of 0 Hausdorff dimension. It's not very large, but there is a set where all the theory doesn't quite work, and the difficulty in showing showing Anderson localization, showing that the spectrum is a pure point, is to show that the eigenvalues do not lie in these exceptional sets. Once this is known, and this was proved, there is a technology to prove this. Once this is proved, the rest of the heuristics is the first part of the heuristics is basically correct, and you get that the rate of decay is at least as fast as it should. So I mean, the initial condition lies in the decay. In the set, the slowest decay is gamma w, so the decay cannot be slower than gamma w. So we get that lim sup of logarithm of psi of n divided by n is less or equal than minus gamma w of lambda, and this is indeed written in the paper of Klein, Lacroix, and Spice. So the question which is not, well, what is not known doesn't seem to be known. So question is the reverse direction. Any questions? Questions?
No questions.
So let me tell you what is known. Let me tell you what is known. So there is a very simple argument, I guess. I mean, what I write now doesn't literally appear in the paper of Craig Simon, but I guess this is the correct. They made the crucial observation that something that should be true. And the observation is that at least, I mean, they studied the case W equals 1 as we saw the singular values can be the first singular value can be much smaller than prescribed by the Lyapunov exponent, but it turns out that it cannot be larger than prescribed by the Lyapunov exponent. So formally, I'll write it immediately for all w's. The upper limit of 1 over n times the logarithm of, let's say, the norm of the transfer matrix is less or equal than gamma 1 of lambda. It may be strictly small. I mean, the lower limit can be strictly smaller, but it can never be large. And this again holds with the right quantifiers simultaneously for all real lambda. So in the case W equals 1, this means that no solution decays faster than the gamma 1, and therefore the equation is settled. This and what I've told you earlier implies that indeed the limit of logarithm of psi of n is equal to the minus gamma 1, where gamma 1 is the only Lyapunov exponent that you have in for the pure 1D case. Whereas when the strip is wider, the only thing which we get from it is that the inferior limit, the lower limit of 1 over n logarithm of psi of n is greater or equal than minus gamma 1 of lambda. So you see the upper bound, in the upper bound, an eigenfunction decays at least with the rate gamma w, and no faster than with rate gamma 1. And by the heuristics which I've tried to explain earlier, it's the first bound, that is, it's this bound that we expect to be inequality. The exponents are distinct, so there is a gap between what is there is indeed for any w, there is a gap between this lower bound and what is expected, and as far, at least to the best of my knowledge, there have been no improvements on this trivial bound since the 80s. Okay. Any questions? Is it clear what is the gap which annoys us? So let me state our so we made this. What I would like to report is some progress on this problem. As you'll see, it's not a full solution, but at least something. So we are as I said, for w equal 1, there's nothing to study, so we'll assume w is greater or equal than 2. And let's also assume that the distribution is absolutely continuous with bounded density. This can be relaxed, but I don't think we can handle Bernoulli at the moment. Then there exists an explicit and deterministic, but somewhat ugly function, which I'll denote gamma tilde of lambda, which is strictly less than gamma 1 of lambda for all lambda, such that the following holds. the lim_inf of 1 over n logarithm of the norm of psi of n is greater or equal than minus gamma tilde of lambda. So it's a strict improvement on what was earlier known. And at no points, if you look at the eigenfunction, you can't have any places where it's as small as e to the minus n gamma 1 as one could naively think. If you are interested in a more modest question, can an eigenfunction always decay faster than gamma w? Then we can answer it fully. So if you agree to replace the lim_inf with lim_sup, then we can prove that this is exactly equal to minus gamma w, as it should be. But for the lim_inf, we only have some improvement over the previously known bounds. And this is true with the right quantifiers, again, for all eigenfunctions, eigenpairs lambda and psi with probability 1. So this is the theorem. Any questions? So at the moment we can't handle Bernoulli, and I can't really say. So something is it's not a technical matter. There's really a place where we use but what I would like to describe in some more detail is the connection between this and somewhat amusing problem in the theory of random matrix products. So the next thing I'll discuss. So let me mention it's a question about random matrix product. So as I've told you, all the smallest singular value of the transfer matrix is very unstable. At some points, it doesn't grow exponentially at all. In this, the question is, what about the other singular values? So I'll write it somewhat provocatively as a question, but I don't have any strong. I mean, I don't really believe that the answer to this question is always positive. But just to make clear, I'll write it in binary form. So is it true that all the other singular values for j less than w, as j is stable in the sense that 1 over n times the logarithm of sj of phi n of lambda converges to gamma j of lambda simultaneously for all real lambda with probability 1. If this is false for j equals w, the question is it true for other j's? As that, I don't have a firm opinion. I believe that sometimes it's wrong, and Grodetsky and Clepson that also worked recently on related problems, ran some simulations, which also indicate that this is probably sometimes false. However, the question is interesting in my modest opinion, regardless of whether the answer is positive or negative. In particular, if the answer is negative, if the answer is positive, as I'll tell you in a second, this will have applications to this problem. If the answer is negative, it will have some amusing applications to the Hadana-Nelson non-Hermitian random operator in a strip, which I won't dwell on at the moment. Let me call it theorem prime. This is a much okay. So if the answer to this question is positive, so if the answer is yes, well, and we still assume bounded density, then also the conjecture holds. this is a somewhat funny conditional theorem, and I wouldn't state this at a respectable seminar like this one. The only reason why I do state it is first to explain the connection to this problem, and second to the idea of the proof of the true theorem is somewhat similar to this one, but involves several additional arguments which are not very complicated but somewhat messy. So since I would like to show you a sketch of the proof, I will sketch the proof of this instead of the original theorem, and then then I'll just mention where I use this assumption and what do you need to do when it's not there. Okay. So if there are, so what I plan to do in the remaining time is to show a sketch of the proof, but first I'll answer questions if there are. How much time do I have?
So there's still at least 15 minutes.
So when should I pass to, when should I stop at 5 to?
Normally at 5 to the hour, but you can go a little bit beyond.
No, that's fine. Okay, so let me indicate a sketch of the proof. So as I've told you, the main issue is with the union bound on a continuum of null events. So how in general do you prove that the union of a continuum of events is usually usually doesn't happen when each of them separately has I'll I'll discuss it now in a very oversimplified setting, but I think it captures the essence. So let's say we have a random subset of the interval 0, 1. I don't enter sigma algebras and I don't explain what does it mean to have. I think it's clear that one can define there is a notion of a random subset of 0, 1. And we want to show that with probability, the probability that it's non-empty is much smaller than 1. Of course, this implies that for any lambda in the interval 0, 1, the probability that lambda lies in A is very small. But the reverse implication is clearly not true. If for example, A is one point randomly chosen in the interval, then the probability that a fixed point will lie in the set is 0, but it will always be non-empty. So what do you need to know if you want to show this, and you can only prove statements of this form? There are basically two ways. Both of them are quite standard. One is common in functional analysis, which uses epsilon nets. Well, in the case of 0, 1, an epsilon net is a very simple notion. Another argument, which is which in this case is almost the same, but in sometimes they're in more complicated situations they're a bit different. Is used, for example, in the work of Kakutani on traces of Brownian motions, and it's explained nicely in Michael Eisenman's article on the renormalization group from the 80s. And again, I specify to this very toy setting. So assume that not only we know this, but we also know that the probability that lambda is eta close, that the distance between lambda and A is less than eta is small. Then the probability that A is not empty is clearly bounded by P divided by eta. So once so the goal should be, if you want to prove something like that, to make sure that you can prove such an estimate with p much smaller than eta, with the probability being much smaller than kind of the distance to which you can extend your estimate. In other words, what we want to do. What we want to do is find a random superset A plus, which contains A and also contains the eta neighborhood of each point of A, such that not only the probability to lie in A is small, but also the probability to lie in A plus. And we actually wanted to be much less than beta. So the interesting question, at least in this problem, I mean, this is a bit naive, but I think it captures the essence. So the interesting problem in this case is how to find this A plus. Usually, at least in functional analysis, many times A is defined by some inequality, and A plus is defined by the same inequality relaxed, let's say, with a factor of 2 on the right hand side, and this works great. So here at least the main interesting point of the proof is exactly the construction of this A plus. And this is what I will try to show you. Sketch of this theorem prime. So L focus on W equals 2. I fix an interval in the spectrum. What we want, we make this assumption that all the exponents except for the slowest, well, I mean, in this case there is just one exponent to gamma 1. We assume that gamma 1 is stable, the norm is stable, and we want to show that psi of n is greater than e to the minus gamma 2 times gamma 2 times n. So rigorously speaking, we have gamma 1 of lambda, we have gamma 2 of lambda, and we need to prove this for any function gamma of lambda which lies between them. I will assume for now that gamma 1, gamma 2, and gamma are constant on I, that gamma 1 and gamma 2, I'm sorry, what did I write? Show that this is less than this is greater than gamma and gamma of lambda times n for any gamma which is between gamma 1 and gamma 2. Rigorously, these should be functions. I will assume that all of them are constant in our interval. This is really not a big deal. I choose the interval small enough to ensure that the variation of gamma 1 and gamma 2 is small enough compared to that. I mean, this is not a big deal. It just simplifies notation and allows me to get rid of to make the formulas a bit shorter. So I have gamma 1 and gamma 2. I fix an arbitrary gamma in between, and I want to prove that this inequality holds almost surely, at least for n large enough. So in the previous notation, it's clear that we want to choose an. Our bed set is the set of lambdas for which there exists a vector set as in this. So remember, F is the space of initial conditions. S of F is the unit sphere of F, and the set n is the set of spectral parameters for which there exists a legal initial condition for which the decay after n steps is faster than what we want it to be. We want to prove that this is not. We want to prove that this the probability of the probability that this an is non-empty is small. We want to show that usually an is empty. So we need to construct an plus Pn and eta n in the notation of the two argument which I told you about. Let me introduce, so let me denote by epsilon, let's say 1/100 times the minimum between gamma 1 minus gamma and gamma minus gamma 2. This is just imagine it's an auxiliary, very small parameter, not depending on n. And then the main point is how to choose an plus. So I will choose an plus to be the set of lambdas for which the projection of the fastest of the direction of pure fastest growth on the space of initial condition is very small, in the sense that it's minus n times gamma minus gamma 2 minus epsilon. Let me explain, let me draw a picture and explain a bit on this, the last thing I'll say, why this choice is somewhat surprising. So we have this fastest decaying direction in the decaying plane, and then we have the growing, the pure planes of the plane of pure growth. So what we assumed is that there exists in F some vector which decays faster than generically. So a priori, our direction of this vector could be u4, for example. The direction, this vector v for which the decay is in F, for which the decay is faster than we want it to be, could be, for example, u4. So okay, we know that u4 lies in F. But why does the projection of u1 onto F have to be small? Why cannot F be spanned by u1 and u4? Right. There's no we know that in F there is one direction of decay. But why can't we have in parallel a direction of fast growth? This basically means that on all of F, not just on our one-dimensional line, but on all the two-dimensional space, we don't have the generic growth. So I mean, namely, why can't F be the span of u4 and u1? If F is, I mean, what is not clear a priori is why is an itself contained in n plus, not to speak of an eta extension of n. My time is over, so is almost over. So let me say that the fact that n is contained in n plus is I mean, at least to some technical matters, is due to the symplectic structure of the problem. The subspace F is Lagrangian, so it cannot contain two vectors obtained one by another by symplectic rotation, and these vectors u4 and u1 are obtained from one another by symplectic rotation. So if u4 lies in F, then u1 cannot lie in F, and a slightly more sophisticated version of the same argument shows that literally the existence of one fast decaying vector in F implies that none of the vectors is growing fast. Then you need a bit more. What we need is that an plus eta n. I haven't told you what eta n is, and I won't tell you. I think this is contained in n plus. This if we have stability, I assume stability. If we have stability, this follows from perturbation theory, and this is, I mean, once you have the first one is a kind of mysterious identity. I mean, simple but somewhat surprising identity involving the symplectic structure. Once you have it, then the rest is less surprising. The extension follows from some perturbation theory, and the bound. The third thing we need is the bound of the probability that lambda lies in n plus. there is some technical matter there which requires some real algebraic geometry to prove, but I don't think I have time to explain it in detail. So I will stop here. Okay, thank you very much.
Thank you very much, Sasha, for this very nice talk. Other questions?
I would have a question.
Yes, please.
Is it possible to translate your result to a lower bound on the expectation value of the fractional power of the Green's function?
At which value of the spectral parameter?
I mean, we know that you have localization at all values for this model. So
the expectation. No.
Yeah.
I think this is what you are asking is known without our result. I think
a lower bound.
I think we're in the expectation. I believe it's okay. I haven't thought about it, but I would think that all the difficulty here is that you want something which holds with probability 1 at fixed lambda to hold simultaneously for all lambda. If you are taking an expectation, then I would think that you don't capture this difficulty, and I would think that this should be known in a strip. But I'll give a more responsible answer when I think offline, at least for 20 minutes. But I would think that this avoids that your question avoids the difficulty which we have here.
Thank you. And also, all you described, does it depend on the particulars of the model, or could you work also with the Wegener W orbital model?
Yeah, no, we don't use. Yeah, that's fine. As long as you can the Wegener orbital or a strip, the cross sections of which are 5-dimensional or whatever you would. As long, in some sense, the real algebraic geometry, which I briefly mentioned, is required to show that the transfer matrices have bounded density with respect to the Haar measure. This is somewhat unobvious and unclear for usual random Schrödinger, since a one-step transfer matrix lives in a submanifold of much law of dimension W inside a manifold of dimension W squared. So you need something. If you are in the Wegener orbital, then probably you don't need this at all. You immediately, the one-step transfer matrix already has bounded density with respect to the symplectic Haar measure, and therefore one piece of the proof is unnecessary. But all the rest is the same.
Thank you.
Thank you. Are there further questions?
Hi, I'd like to ask a question. Thanks for the nice talk, Sasha. Suppose you finish this up and prove this conjecture. Are there implications for this model? For example, can you say anything as W, the width size, gets large? This was one of the big open problems from the 80s that I think was never resolved.
I'm interested in this question, but I'm not aware. I think I find this question which you mentioned very interesting, but I don't know of any direct connection between it and what. And I don't think. So one question is how do the Lyapunov exponents behave, and the second question is how do they control the spectral behavior? I'm not aware of a formal connection, but but well, okay. At least immediately, I can't. There's nothing positive I can say immediately. But
I mean, aside from proving a really nice result, is there other motivation you had for improving this behavior, getting the optimal behavior?
I mean, the motivation is to understand how the Anderson localized eigenfunctions look. In particular, whether they have an exact rate of exponential growth. I mean, the question, I can't, I mean, okay, for example, no, I don't. I mean, I think the question is so for me the question is so simple to state that it kind of motivates itself. I don't think it implies it implies any other known conjectures, and definitely I don't think that this is really a question for fixed W, and I don't think it has an intimate connection to any questions concerning the large W asymptotics, which are probably which have a different difficulties in them, but yeah.
Yeah, well, thank you. Yeah, I agree. It's definitely a very nice question. Good luck in resolving the rest of the conjecture. Hope it works. Thank you.
Further questions?
There was someone raised a hand, but he didn't.
I did not, but no longer.
I have a naive question. So these Lyapunov exponents of products of transform matrices, are they easy to compute? I mean, they don't sound as something very explicit. I mean that.
No, they're impossible to compute. They're impossible to compute except for some strange cases, such as the Lloyd ensemble or whatever. No, usually they're impossible to compute. But the main thing is that it's a deterministic quantity depending nicely on continuously on lambda. I mean, in dimension 2, there's no notion of Lyapunov exponents, but the question still makes sense. Is there a deterministic rate of decay which depends on the position on the spectrum? Since I don't have anything to say about that, and we're studying the strip, and the strip, it's clear it happens to have a name, and there happen to be some tools to study it, but yeah, that's. No, it's not. It's indeed it's not explicit in any way. I don't know. I'm not aware of examples where it's where W is greater than 1 and one can compute it precisely.
And I wanted to ask you more about this piece of real algebraic geometry. Well, I mean, seldom this area of mathematics is useful in such problems.
So what was not obvious to me, perhaps it's not very hard, but I don't know any proof which avoids some amount of algebraic geometry. At least maybe it's not very complicated, but it requires something. One transfer matrix depends on on W values of the potential, so it lies in a W-dimensional manifold inside the symplectic group. Now the question is it true that after multiplying 25 independent copies of this, you have a distribution which has full support and which has bounded density with respect to the Haar measure on the full symplectic group. If the situation would be commutative, if we would work in an abelian group, usually such questions are resolved by Fourier transform. You establish some amount of Fourier decay, and once you have some power law Fourier decay, you convolve sufficiently many times, and you get Fourier decay, which guarantees absolute continuity. In the non-commutative case of the symplectic group, I don't think this, first of all, the representation theory of the symplectic group is quite complicated, but also I don't think these arguments are of any, at least I'm not aware of any way to make any sense of these arguments, and one needs other ideas, and which I've yeah, I have to say I've learned from Itai Glaser and Yotam Hendel, who studied such problems for some other number of theoretic reasons, and developed some nice arguments which turned out to be useful here too. Yeah, so that's the question is very simple about regularization by convolution, but since it's in a non-commutative Lie group, I don't know how to solve it without any algebraic geometry at all.
Thank you. This was a beautiful talk, I must say.
Thank you. Further questions? So maybe one question. So to go back to this question of Peter about whether the limit W going to infinity would go to Z2. So perhaps you could also try to add another strip in order to get somehow closer to Z3. Would things change a lot?
I can definitely, yes. Someone asked this before I managed to establish a one-to-one correspondence between the speakers, and it doesn't matter at all that the strip has this form. It doesn't matter what the cross section is. I stated it for the strip, but if you prefer two-dimensional or five-dimensional cross section, this is fine too. The proof works. I mean, in the text which we posted an archive, it's stated in greater in a generality which includes all these cases as well as other ones. You need a condition. You need a condition that somehow you're not. I mean, what you don't want is two strips which are not connected to one another. Kind of non situation when the transfer matrices are not the risky dense in the symplectic group. This definitely cannot work. Once you exclude it, you're fine.
Thank you. One last question, perhaps. If not, let us thank Sasha for this beautiful talk.
So I would maybe, maybe one more question. Could you, just
yes,
for the sake of completeness, could you spell out what the conjecture would be for the asymptotic behavior of gamma W as W goes to infinity? Is it 1 over W? Or?
Yes, it should be 1 over W.
For the Wegener W orbital model.
For random Schrodinger in a strip.
So how would you recover a complete 2D localization?
No, it's a bit subtle. There is you look at a strip. It's not very easy. You look at a strip. It has length L, a finite strip, and width W. Somehow the Lyapunov exponents control the behavior. I mean, the limit when L goes to infinity and W is fixed, but at least presumably the Lyapunov behavior kicks in when L is greater than something like W log W. I believe that when L is satisfied, or something like this, then the singular values are now in order. Of course, there is the other regime when L is, let's say, smaller than W divided by some logs, where your random Schrodinger looks delocalized. But in order to study the critical behavior in 2D, where you expect localization by whatever normalization group theory, you need L to be equal to W, and there is physicists do have a scaling theory which tells how to glue this regime to this one in a smooth way, but it's not trivial, and I don't think I can explain it in a minute. The DPSK Dorohov. There is prediction how these two asymptotic regimes are good, but indeed you don't immediately see from where the conjecture that gamma w behaves like 1/w lives here and doesn't immediately tell you anything about this point.
Thank you.
Thank you. So let us thank Sasha for this beautiful talk. We can stop recording.